So I appreciate the opportunity to discuss arc flash and EasyPower. And what I plan to do today is cover some ground. A little bit has already been touched on by previous presenters, but I want to work through who's at risk, what entails an arc flash risk assessment, and then something that's puzzled me since I've been with EasyPower is why people delay compliance for something that's recognized as a hazard. For those of you that don't know, EasyPower produces software for engineering analysis of power systems, and this includes arc flash, and we also do training and engineering services for some of these studies. Arc flash presents a number of hazards that can be harmful to humans, ranging from heat that approaches the temperature of the sun to toxic gas, pressure wave potentially because we have vaporizing metal that can throw projectiles 6 or 8 feet. It creates almost always a fairly significant sound level. One of the most common symptoms for everyone complains about after being exposed to an arc flash event is how long their ears ring afterwards. And then obviously there's very intense light. Now the point that I would like to make is that when we talk about PPE for arc flash, we're really only referring to protection against the heat itself, and knowledge of your system and whether or not there's other hazards may be present is something that should be included in your assessment. And one of the things I like to start with is an accident report from OSHA that I found on the OSHA website and was captured in a CCTV frame from the original event. So I'm reading here directly from the accident report. A crew of electricians and facility personnel for a Wisconsin meatpacking plant had completed an annual cleaning of electrical utilization substations 1 and 2. To facilitate cleaning, the plant was switched from outside utility power to emergency generators, and after the substations were cleaned, the process to switch back to utility power was started, and they had a problem with the transfer switch that was inside this particular cabinet. So we have facilities personnel and management trying to debug or understand the problem with a 1 horsepower, 120 volt motor that was driving the transfer switch. And inside this cabinet was a 13.2 kV bus as well. So here's what the closed circuit TV captured. And so there's a number of things I like to discuss that impact the arc flash situation. So here we are 10 seconds after the event, and there's still someone pulling smoldering clothing off his body. And this is evidence or symptom that the material was synthetic and had melted, holding the heat closer to his person than necessary. Obviously, none of the 3 had on proper PPE. And I like to go back to a single frame and kind of analyze some of this that impacts the calculations of arc flash. So even though the timestamp is fairly gross or coarse, you can see that the arc flash itself lasted much less than 2 seconds. And industry pundits have estimated this event was probably somewhere in the 12 to 15 calorie range. This sphere, this white sphere that looks like it's maybe 6 to 8 feet in diameter, this is the fireball that exposed all 3 to burns or heat. And all 3 went to the hospital with body encompassing 2nd and 3rd degree burns. One had to stay an extended period. But inside this fireball is the plasma ball, which probably measures anywhere from 1 inch to 3 inches in diameter. And it's what produced the heat and the pressure wave that they experienced. And it's interesting to point out this white vertical area up top. This is evidence of the reflected energy from the back, bottom, and sides of the cabinet, since they were looking at the only opening of a six-sided cube. As I mentioned, all three went to the hospital. The accident report in OSHA reported that the company was fined $140,000, and the report has several references to a willful disregard to employee safety and lack of PPE for personnel. In the period from 2003 to 2015, there were reported approximately 2,300 fatalities in the industry, and most of these were in the industrial marketplace, the only exception being those in the power line segment. During that same period of time, there were approximately 24,000 non-fatal injuries that required medical attention, and then estimations in the industry of 10 times that number for events that were not reported but were near miss and required less medical attention. The point being is that this is still a significant hazard and should be of concern to facility owners. So there are several standards or levels of overlapping responsibility in electrical safety. So at the top, there's the OSHA regulations and requirement that can be enforced by law. And there's a number of consensus standards that can be used as guidance for OSHA compliance. In the electric utility industry, there's the NESIC documents. There's the National Electrical Code for construction and installation. And in general industry, the standard for electrical safety in the workplace is NFPA 70E. And in Canada, that's mirrored by the Z462 documentation. And most of these don't just dictate specifically what guides or methods should be used for calculating arc flash, but what we focus on is regarded as the national standard recognized internationally is IEEE 1584, because it's based on test data that was generated by IEEE and industry partners. If you want to know how OSHA gets into the Act, above all else, they have what's regarded as the general duty clause that dictates each employer shall furnish to each of his employees a place of employment which are free from recognized hazards. And so most of my time is spent making sure people understand arc flash is a recognized safety hazard. And if such hazards are present or likely to be present, the employer shall select and have affected employees use types of PPE that will protect them, communicate the selection decisions to each affected employee, and select PPE that has proper fit and application. Now, when we talk about consensus standards, this is the section in the OSHA documentation that refers to the consensus standards, and that is the relevant legislative history of the Act indicates a congressional recognition of the American National Standards Institute and the National Fire Protection Association as major sources of consensus standards. The footnote here is these are not law, but they give you guidance into how to comply with the law. So employers following the consensus standards can make a pretty good case that they were meeting at least a minimum of requirement for OSHA documentation. So the bottom line for electrical safety in the workplace is NFPA 70E, and it identifies the responsibilities of employers and employees as follows. The employer shall identify the hazard, provide safety-related work procedures, train employees in the practices, supervise the employees, and audit and document the results. The employee, on the other hand, must be able to recognize the hazards and apply work procedures accordingly, and then comply with training and demonstrate ability to do so. This document includes procedures for hazard risk assessment that include electroshock and electrical burns. Now, the basis or the background of assumptions for applying the recommendations in NFPA 70E is what's defined as normal operating conditions. And this includes that the equipment must be properly installed per manufacturer's instructions, properly maintained per manufacturer's instructions. The equipment must be used in accordance with manufacturer's instructions. The equipment shall have covers, doors in place and secured. And probably as important as anything else, there's no evidence of impending failure. The bottom line is, if we can't answer each of these in the affirmative, we need to make sure that we understand how that affects the calculations that are being done or the assessment, the hazard that's being made in terms of our need for maintenance. So the bottom line, or the prime directive in NFPA 70E, is thou shalt not work on hot equipment. Obviously my own paraphrasing. But that means that we need to establish an electrically safe work condition. Well, even when this is a company policy, and that is we don't allow people to work on hot equipment, that doesn't mean that you eliminate the need for an arc flash risk assessment. And the reason for that is PPE must be worn to test the equipment before we can approach it and understand that it's been electrically secured. So NFPA 70E, as I say, directs that de-energized work is the only safe work condition, but they give us three categories in which electrical work can be done while the equipment's energized. First is when the voltage on the equipment is less than 50 volts. So this is how telecom equipment can be operated and debugged and worked on without de-energization. The second is when de-energizing the equipment introduces additional hazards, which you would expect to see maybe in a medical equipment where there's life support equipment, or emergency alarm systems, or equipment that needs to be up 100% of the time. And then finally, when the permitted task is infeasible in a de-energized state. And this goes back to the operating conditions. If one of the requirements for equipment manufacturing maintenance is to be able to inspect, adjust, or otherwise test equipment that's energized, we can't very well do that. And so that exception is referred to as infeasible. And so each of these electrified conditions, the two statements or categories where we could do electrified work, needs to be done under the auspices of a hot energized work permit. NFPA 70E also approaches or talks about electroshock hazards, and these are a lookup table, if you will, based on the voltage on the exposed bus. It's probably important to notice that these boundaries don't exist when I have the equipment closed up. It's only when the door is open or the panel is removed that humans exposed to bare conductors that are hot, and at which time these boundaries appear or become in effect. Now, NFPA 70E also defines what the arc flash boundary is, and this is under the definitions category. And that is when an arc flash hazard exists, it's the approach limit from an arc source at which the incident energy equals 1.2 calories per square centimeter. Now, this is not a number that's been picked out of the air. It's actually the result of studies that were done by exposing human skin to different levels of heat flux. And it was determined that 1.2 calories per square centimeter for 1 second was the level of exposure. There was a 50% probability of second-degree burn. Now, as was mentioned earlier, there's a couple ways to determine arc flash boundary and PPE with a lookup table. And then there's also the incident energy calculation method. Obviously, that's what I'm focused on. And The bottom line is to determine the appropriate safety-related work practices required for the equipment, the arc flash boundary, and then the PPE used within the arc flash boundary. And this must be documented as a result of the study. So an arc flash risk assessment basically consists of collecting the system data, creating a one-line diagram, which is a digital file that incorporates this data, then conducting a short circuit analysis to determine the maximum current at any particular location in the system, and then calculating instant energy as a result of how the overcurrent protection devices react to that level of current. NFPA 70E describes two categories of PPE once you've used instant energy, and this requires that the PPE selected must equal to or be greater than the instant energy calculated. And so the two categories are 1.2 calories to 12 calories, and then greater than 12 calories, the primary difference being that below 12 calories, you can use an arc-rated balaclava. Above calories, it's required to use an arc flash hood. The arc flash assessment is not the first and last step in an electrical safety program. It's actually the beginning of an entire cycle that needs to include labeling, maintenance, PPE selection and use, training of personnel, auditing the system as we use it, and then incorporating updates both in our organization and our facility, as well as the standards being used. NFPA 70E Article 130.5 requires that equipment such as switchboards, industrial control panels, and motor control centers that are likely to require examination, adjustment, or servicing while energized require field labeling. And the label shall contain nominal system voltage, arc flash boundary, and at least one of instant energy and working distance or the PPE from lookup table, but not both. Here's an interesting question. Who's responsible for updating information on the equipment labels? And this question actually came in from an engineer working in an automation assembly plant. He was getting inputs from several different directions and was wanting to know who he should listen to. Well, according to NFPA 70E, the owner of the electrical equipment shall be responsible for the documentation, installation, and maintenance of the marked labels. This brings up another observation, and that is because of this requirement, very frequently equipment installation contracts require that equipment be labeled before taking new ownership of the title per NFPA 70E, because prior to that, the National Electrical Code permitted only a generic arc flash label to be used. Here's another question. How often do you repeat the study? Well, I want to point out that in NFPA 70E, it suggests that any change that occurs that affects the results of the study, you need to update the study, or at a minimum of every 5 years. Comparing that to what's required for retraining, especially in lockout tagout, procedure, if it's revised, people need to be retrained, and or at least every 3 years. The point being, it's recognized that better training, better procedures, documentations, and system controls have more of an effect in preventing accidents as opposed to the arc flash incident, the PPEs being worn, because that just reduces the amount of damage one receives during an event. Here's another question that comes up. Do you have to be a PE or a EE to perform an arc flash study? Well, not according to IEEE 1584. It defines a qualified person as one who can perform arc flash hazard calculations by using skill, knowledge, and has experience in power system studies. Now, when the arc flash study is part of new engineering work, as there may be local codes that require a PE stamp, so you need to be aware of that. Well, as we indicated, I do arc flash workshops monthly, and it struck me at one point in time that industry pundits estimate that less than 20% of US companies have completed a study. Well, it dawned on me, why would anybody delay working on arc flash compliance if it was that big a deal? Well, I compiled a list of possible excuses, if you will. One is cost. It does cost some amount of money to do an arc flash study, but one bad day that involved an arcing fault could end up being 50 times the cost of the original study itself. It does require some amount of time, but you can schedule as time allows, and it is something that you weigh against the safety risk of employees. Obviously, it requires manpower, and emphasis on safety could reduce the turnover if that's one of the problems, but this is something that can be outsourced and scheduled. My advice would be make sure that you find somebody you can trust who's qualified to do studies, and by all means get a digital copy of the model that they use to generate the results. But the most surprising excuse was that our electricians say we don't need it, it's only a problem at high voltages. Well, that brought me to understand the arc flash paradox, and it's a failure for seasoned personnel to understand the counterintuitive nature of arc flash, and it affects the most seasoned techs who don't understand it. And I put myself in this category when I first joined EasyPower. I actually thought I knew everything about Ohm's law, and I had a phone call from an electrician in Oklahoma. He said, "Jim, I've just purchased EasyPower tools. I have to label the above ground distribution system in an oil field, and I think there's a bug in your software." So we got on the phone, and as we talked, I built this one-line diagram using EasyPower. He said, first of all, we want to start a new project. And I'm going to pick up an icon from the equipment palette for the utility icon. And he said, the first thing we have is a utility transformer. So we pick up the 2-winding transformer, touch the pigtails, click again. The tool knows that we need a voltage assigned to this intersection. He said his incoming voltage was 12.8 kV. He said, put a plain bus on the secondary side of the transformer. And again, it wants to know the voltage that's coming out of the transformer. Everything's in kilovolts, so I type in 0.48. He said, extend this bus about half the width of the screen and drop a cable on each side. So the cable is a circle with 3 inscribed circles. Click it once, put the crosshairs on the bus, click a second time, do the same thing on the other side. He said, terminate each bus with terminate each cable with a plain bus. If I want to reuse the icons, I just hold down Control, and I can put buses at the end of each cable. Now, as we're doing this, you can see there's missing data by the asterisks on each of the elements. The first step in doing an arc flash study is a short circuit analysis. If we prematurely try to go to short circuit focus, the tool says, Jim, are you sure you know what you're doing? Do you want to see an incomplete data report? If I say yes, it says, well, I need more information on the transformer and 2 cables. So if we go back to our one-line diagram, I can see that those elements are highlighted in red. I'm going to double click on the first cable. He said, Jim, I've looked at the markings on this cable. It's a single conductor per phase. It's a 1C cable. It's THWN because it's an outdoor run. It's a 350 kcmil size, and it's 50 feet long. Now, what we've just done is describe a copper conductor with this geometry, this installation, routed through a steel conduit, and the tool will auto-calculate my ampacity at 310 amps. He said the second cable has the same construction as the first, so I right-click on the first cable and copy, right-click on the second cable and paste, and all that data is taken to the second cable. He said, Jim, the second cable has the same construction, but it's a different length. So it's actually 1,000 feet long instead of 50 feet long. So again, the tool calculates automatically the ampacity and the resistance or impedance. Everything that's required for the transformers on the nameplate of the transformer. He said, Jim, I've looked at the nameplate. The transformer is oil-filled, class OA, works with a fixed 65-degree rise. It's the delta Y with the Y grounded, and it's 1,000 kVA. Now, because I've done this before, I know there's mandatory data on the impedance tab. It said the impedance ratio is 5.75%. and the tool will calculate the X over R and zero sequence ratio for me. Now, the reason I like this example as much as I do is there's one protective device in the system, and he said it was a fuse in the electrical cutout switch. So I pick up the fuse switch, open up the dialog box. EasyPower has a device library that has the data for each cable and the transformer. And now we're going to enter the data for the fuse. There's a device library with 40,000 entries in it, and every fuse, relay, and breaker is in that category, in that device library. I want to make sure that my one line is connected to the correct data sheet. So the electrician said, Jim, I've opened up the cutout switch and looked at the label on the fuse. It's an AB chance fuse link. The model is a Model T, and we chuckled because we thought a Model T is in a different context, and it's the size 12. And this is a true conversation. So when I go to short circuit, I want to connect to the device library by hitting calculate. The fact that this number comes back with 15, the tool says I've found the device data sheet for this part number. The manufacturer tested to an ANSI standard, and the X over R environment at the test fixture was 15. The reason that's important is EasyPower will calculate the X over R at every bus, and wherever there's a protective device, it will compensate for the difference between the manufacturer's test environment and our installed part. So now he's ready to go to short circuit focus. We're on the top row. Look at the half cycle, 3-phase bolted fault, and fault all the buses. And what we're looking at is just the A phase. We can look at all 3 phases, but because we defined it as a bolted fault, they're all the same. He said, Jim, this makes sense. Well, it doesn't make sense, but we'll deal with it. Let me double check my, oh, I got too many 5s in my transformer. Okay. Go to short circuit, fault all the buses. He said this makes sense. If the transformer secondary was faulted, each phase will see 20,915 amps. If the 50-foot panel was faulted, I see 17,878 amps. And if the 1,000-foot panel had a 3-phase bolted fault, each phase will see 4,351 amps. He said, now I'm ready to calculate instant energy. The instant energy icon is this little burning man symbol on the top row. And once I click on that, I get new numbers and new colors. And he said, Jim, this is where I have a problem with EasyPower. I said, well, what are you talking about? He says, right here on the transformer secondary, I see an arc flash boundary of 27.4 inches with an instant energy of 2.3 calories per square centimeter at a working distance of 18 inches. So I know I can work on this bus safely with the 4-calorie PPE. But if I walk to this bus 1,000 feet away, my arc flash boundary is doubled, my instant energy is almost tripled, and you're telling me I need to put on more PPE to work on this bus hot. How can that be? I said, Vern, I don't understand what you're saying. What are you trying to tell me? He said, Jim, I've been an electrician for 25 years, and anybody that works in electricity knows the farther away you get from your energy source, the lower the energy is going to be. You're telling me this energy goes up. How can that be? Well, my response was, I've been an electrical engineer for 25 years, and I agree with you. I don't see how the energy can go up. The reason for the story, and this was an actual conversation, is to show the advantage of the tools. Because at any point you're doing an analysis, you need to know if the calculations are correct. So the utility that we offer to do that is called the range for arc flash icon, which allows me to look at the one-line diagram and the way the calculations are being made in the tool. And so if we highlight the transformer secondary, we see it's a 480 volt bus. The fuse is a protective device. The air gap, let me modify my report. The air gap is 32 millimeters. We knew the bolted fault current. The arcing fault current is 13.664 kiloamps. According to the data sheet for that fuse, it'll take it 67 milliseconds to clear the arc. And that gives us the instant energy of 2.3 calories at a working distance of 18 inches. If we walk 1,000 feet away and have a fault on this bus, it's still 480 volts. It's still the same fuse. It's still the same air gap. But now the maximum current that an arc will draw is 2,729 amps. That means it will take almost 1.5 seconds for that fuse to clear the arc. What that means is if we wore a 4-calorie PPE when we worked on the transformer secondary, and we came down with that same PPE to work on this bus and accidentally induced an arcing fault, the energy released during that 1.5 seconds will be 20 times, well, the time is 20 times longer. And so our little 4-calorie PPE won't be enough to protect us against that radiated heat. And both of us went, duh, I get it. Time is everything when it comes to arc flash. So my point being that there's a failure for most people that haven't done a study to understand the counterintuitive of arc flash itself. And so the bottom line is you cannot determine an arc flash hazard just by looking at it. Time is everything. And when it comes to arc flash, the key results of the study need to include the arcing current, the arc time, and the PPE. I appreciate everyone's attention today. I'd like to let everyone know that we do a free monthly arc flash workshop. There's no cost. It includes 2 weeks of free use of the tools and follow along examples that we do in a 4-hour presentation. And you're more than welcome to download the free arc flash manual that's online. So I'm ready for questions if there are any.
So the first question that I've been wondering about for a long time is, I get many calls and comments from people asking me whether or not they can do their own arc flash study.
The answer is yes. All right. And that's why I put in there's no certification recognized by anybody so far, but it requires experience. And so the question is, where do you get experience? Well, and that's why we provide services for people that are trying to do their own study as a technology backup.
Yeah, because a lot of companies don't allow their engineers to do their own studies. That's the other thing that that has come to me over the years, that they prefer to use an arc flash study consultant as opposed to doing it themselves for a couple of reasons. One, because they think they can't afford that software to do it just once, to do a study just once, and also the management doesn't trust their own engineering. They think that if a consultant does the study for them, it's a better study. What are your feelings about all of that?
I'd add one more reason to the list, and that is liability.
Right.
And it turns out that's probably that should be the least concern. And the bottom line is most of the heavy lifting is done with the software itself. So in my mind, a very critical part of the whole procedure is data collection and knowledge of their system. And frankly, it's difficult for a third party to be that involved unless they spend a lot of time with the operating personnel and maintenance, all of which is a good idea and should be part of a complete study. So the pendulum swings either way. There's good and bad on each method. And the bottom line is you'll know more about your own system the more involved you are at each phase of that study completion. And so some people do their own data collection and then hand off that to the third party to do the study analysis. But the bottom line is, what do you do with the report once it's done? And if you don't take action on the results, it didn't matter who did the study.
Well, you're right. Absolutely. All right. What I was mentioning earlier in the forum today that over the last 20 years, many companies, many industries have performed arc flash studies on their equipment. But I know that many companies think they just have to do that once.
Right. And that's a fallacy. And that's what one of the advantages of having control of the tools and the original database yourself is that updates can be made as the system changes. And the advantage of understanding how the process works and the mechanics of using the tools gives you some insight into where your technical knowledge has limits and it's time to reach out for additional resources. So the standard says it needs to be updated at a minimum of every 5 years, and or anytime the system changes that affect the outcome. And you can't tell that just by looking at the equipment.
Right. Okay. And one last point about that. Is it true that only 50% of companies have an up-to-date single line?
I would guess it's even less than that. I actually visited a company in the Seattle area who's a primary supplier to Boeing. And when I was talking to the facility manager about their one-line diagram, he said, we don't have one. And theirs is a big organization. It's like, how can that be? And his answer was, well, during the downturn, they laid off all the maintenance people, and they were the ones that had the knowledge of the system. And so he was brought on board, and his first task, his first priority was developing the one line. And it took him a better part of 3 years just to get the first pass at completion. So yes, it is true. And it's dangerous. You can't have a modicum of electrical safety if you don't have a up-to-date one line.
Yeah, I was surprised to learn that Vancouver Airport and San Francisco Airport didn't have an up-to-date single line, and they had to hire engineering companies to do it for them.
Yeah, exactly. And this is all, and that's the problem. People get used to using reference to the National Electrical Code, which allows grandfathering in of previous work, which is not true with NFPA 70E, because the standard becomes effective the day it's released. And so if I don't have an up-to-date study, I'm at risk at that point.
Okay, let's look at the questions now. Shouldn't there be OCPD on each branch from 480 volt bus? Wouldn't that rectify high AFR? You know, I don't know what those acronyms mean. So maybe you can explain that to everybody.
Well, the answer is yes. And the problem is older systems like airports, like pumping stations for the Forest Service, they were designed 25 years ago when you didn't know about arc flash, and it was permissible to have primary protection. So the question goes to, the solution is having in-circuit feeder protection for each load that's sized properly. And yes, you would be able to reduce the arc flash at the load with that device.
Okay.
I mean, that's something, and my point is that's the obvious thing that jumps out at you with using the tool and the knowledge that you're gaining of your system by doing the analysis yourself. Hate to repeat.
That's okay. Is there a tool for voltages over 15 kilovolt?
Yeah, it's included in the EasyPower. Turns out there's no recommendation from 1584 above that. The tool allows us to use or incorporate Ralph-Lee equations, and or for single phase faults to ground over 15 kilovolts on an open air circuit, you can use a single line to ground model, which can go much higher voltage, as high a voltage as there is in the industry, and create an arc flash label for that.
Does EasyPower accommodate both AC and DC arc flash?
Yes.
Okay.
No, it's an interesting point. It's not in 1584 that's covered, but in section D of NFPA 70E, they refer to the Doty equations, and we use the same equations. We refer to it as the max power method.
Good. The arc flash assessment, somebody mentions this is Carlos, the arc flash assessment should be together with the coordination protection study.
So the answer is yes. And if a coordination study has been done and nothing's been changed, in other words, it's a little bit of a gotcha to say, well, we don't need a coordination study. At the very least, you need to spot check to make sure nothing's changed from the original design. So I would agree with Carlos, but that's something that separates a static plant versus a dynamic plant that's had a lot of changes.
Right, okay. Next question. Jim, your example is very common for many old panels that have been installed a long way away from the main bus. Those panels need to be protected. Is there any cost-effective solution to protect those panels? For example, adding rapid fuse on top or changing main breakers with LSI circuit breakers. Any general recommendation?
Well, so there's multiple solutions to it. Cost effective is a limiting factor. The problem with using a main breaker or protection is that you can't count on the main breaker if it's inside the same panel as your bus work. And so that's another recommendation from IEEE is that if you need to have a barrier between the incoming conductors to the main and somebody working on the main bus. And if that's not the case, then you can't count on that device to do protection. So current limiting or anything external to the main breaker is a good recommendation, a recommended solution. Does that make sense?
Yeah, great. Okay, good answer. Can you please comment briefly regarding the 2-second rule for arc flash analysis?
That's a good one. It's been moved from the annex portion of the old standard to the verbiage considering the new standard, and it goes like this. On any system where you have high incident energy due to long tripping times and is permissible for the operator to remove themselves during an arc flash event, then it's reasonable to limit the max calculation time to 2 seconds. But in fine print, and I emphasize this over and over, is that you need to use engineering judgment before you apply this. I personally don't recommend using 2-second max on anything above 240 volts.
Okay.
That's just me.
Okay, Justin, there's your answer. Okay, that's great presentation. Thanks very much. I appreciate it, Jim. Okay,
My pleasure.